Tonight, we're going to explore something that sounds like science fiction, but is actually one of the most certain events in our cosmic future. The red giant. The day the sun eats the earth. You've probably heard this phrase before. Scientists talk about it. Science fiction movies dramatize it. The idea that our sun will eventually grow enormous and swallow our planet whole. But here's what most people don't realize. When you actually understand how this happens, when you dig into the real science, you discover something far more unsettling than any movie could portray. This isn't about sudden destruction or cosmic catastrophe. It's about slow, inevitable betrayal by the very star that gives us life. The sun isn't just going to get bigger, it's already getting brighter, degree by degree, year by year. And Earth's fate will be decided not by fire, but by the gradual loss of everything that makes our world habitable. The oceans, the atmosphere, the delicate balance that keeps us alive. By the end of tonight, you're going to understand why this quiet transformation is already underway, and why it represents one of the most profound truths about our place in the universe. Before we dive in, if you enjoy this kind of deep exploration, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's begin. You wake up each morning and there it is, the sun, hanging in the sky like it always has, like it always will. A golden disk that rises in the east and sets in the west with such predictable regularity that we've built our entire civilization around its rhythm. For thousands of years, humans have looked up at that bright circle and seen constancy itself. The eternal flame, the unchanging light that powers everything we know and love on this small blue world. But you're looking at an illusion. What appears to be a steady, permanent lamp burning in the heavens is actually something far more dynamic, far more alive, and far more temporary than our ancestors ever imagined. The sun isn't a light bulb screwed into the ceiling of space. It's a massive, roiling ball of plasma, held together by its own gravity, powered by nuclear fusion in its core, and it's changing every single second of every single day. It has been changing for 4.5 billion years, and it will continue to change for billions more, following a script written in the fundamental laws of physics. The sun is not eternal. It's mortal. Just like everything else in the universe, it was born. It has lived. And someday it will die. But here's what makes the story of our star so fascinating and so unsettling. The sun's death won't be a sudden event. It won't explode tomorrow or next year or even next millennium. Instead, it will unfold over such vast stretches of time that the human mind struggles to comprehend the scale. And yet, paradoxically, the effects of this slow death are already underway. Right now, as you listen to these words, the sun is approximately 4.5 billion years old. In astronomical terms, that makes it what scientists call a main sequence star, sitting comfortably in the middle of its life cycle. It's been fusing hydrogen into helium in its core for all those billions of years, converting matter into energy according to Einstein's famous equation, releasing the light and heat that keeps our planet warm and drives every biological process we know. From the photosynthesis in a blade of grass to the complex neural activity in your brain, everything depends on that steady stream of energy flowing from the fusion furnace 93 million miles away. But steady doesn't mean unchanging. Every second, the sun converts roughly 600 million tons of hydrogen into helium in its core. Think about that number for a moment. 600 million tons. Every single second. That's more mass than exists in all the mountains on Earth, transformed from one element into another, releasing energy in the process. And here's the crucial point that most people never consider. When you're burning fuel, even nuclear fuel, you're using it up. You're changing the composition of what's doing the burning. As the sun converts hydrogen to helium, it's gradually altering the chemistry of its own heart. Helium atoms are heavier than hydrogen atoms, and they behave differently under the extreme conditions of stellar fusion. This means that as billions of years pass, the core becomes more and more dominated by helium ash, the leftover product of all that nuclear burning. And when the core changes, everything else changes with it. The sun is getting brighter, not dramatically, not enough for you to notice in a human lifetime, or even in 1,000 human lifetimes. But steadily, inexorably, year after year, the nuclear furnace at the sun's heart is becoming more efficient, producing more energy, sending more radiation streaming across the solar system toward Earth. Over the course of the sun's main sequence lifetime, its luminosity will increase by roughly 30%. That might not sound like much, but on a planet where the difference between an ice age and a warm period can hinge on changes of just a few degrees, 30% more sunlight is catastrophic. This is where the story becomes both beautiful and terrifying in its inevitability. The same process that gives us life, that powers every sunset you've ever admired, that drives the weather patterns and ocean currents and seasonal cycles that make Earth habitable, this same process carries within it the seeds of our world's destruction. Not through some cosmic accident or external catastrophe, but through its own success, its own continued operation. The sun isn't going to explode and instantly vaporize the Earth. It's going to slowly, gradually, gently cook us. First through increased brightness that will push our climate past breaking points we've never imagined. Then through changes in size and structure that will fundamentally alter what it means to be a star in our solar system. The most dramatic ending is not the sudden destruction you might expect from science fiction. It's transformation. Slow, inevitable transformation that begins with light, continues with heat, and eventually culminates with size. We live in a universe where nothing lasts forever, not even the stars. But we also live in a universe where change happens on scales so vast that they dwarf human experience, making the temporary feel eternal and the mortal feel immortal. The sun that shines on your face today is the same sun that warmed the dinosaurs, the same sun that will shine tomorrow and for billions of tomorrows to come. But it is not the same sun that will exist billions of years from now. That future sun will be a different star entirely, brighter and eventually larger, following a path toward transformation that no planet in its vicinity can survive. This is the story of that transformation. This is the story of how a star dies, not in violence, but in slow, measured change. And this is the story of what that death means for the small, water-covered world that has, for a brief and precious moment in cosmic time, called that star home. When you imagine the end of the world, you probably picture fire, explosions, dramatic destruction with the Earth consumed in flames as our planet spirals into the expanding sun. It's a compelling image, one that captures the imagination and appears in countless stories about our cosmic future. But this vision of Earth's final moments, as dramatic as it might be, misses the real story entirely. The truth about how our world will end is both more subtle and more profound than any Hollywood catastrophe. Earth's fate will be decided long before the sun ever grows large enough to physically engulf our planet. Billions of years before any possibility of direct contact with the solar surface, long before the sun transforms into the red giant that dominates our imaginations, the conditions for life on Earth will have vanished completely. The day doesn't end in fire, it ends in brightness. This is perhaps the most counterintuitive aspect of Earth's future. We tend to think of the sun's expansion as the primary threat, imagining our planet gradually approaching an enormous, bloated star until the two finally meet in a dramatic collision of world and sun. But the real drama unfolds much earlier, much more gradually, and involves not the sun's size but its energy output. The sun is already in the process of destroying Earth's habitability, and it's doing so through the very same mechanism that currently sustains all life on our planet. Every day, approximately 174 quadrillion watts of solar energy reach the top of Earth's atmosphere. This is the energy that drives our weather, powers photosynthesis, creates wind and ocean currents, and ultimately sustains every biological process from the smallest bacteria to the largest whale. But this energy input isn't constant over geological time. As we've seen, the sun is gradually brightening as its core composition changes, and this brightening will have consequences that unfold across a timeline measured not in millions, but in billions of years. The first casualties won't be mountains or continents or even large ecosystems. They'll be much more fundamental. They'll be the basic physical and chemical processes that make Earth a habitable world. And the front line of this cosmic battle won't be on the ground. It will be in the atmosphere, in the oceans, and in the delicate balance between water in its liquid, gas, and solid forms. Water is the key to everything, not just because life as we know it requires liquid water, but because water vapor is one of the most powerful greenhouse gases in our atmosphere. This creates what scientists call a feedback loop, and it's this feedback loop that will ultimately determine Earth's fate. As the sun grows brighter and pumps more energy into our climate system, more water evaporates from the oceans. That additional water vapor traps more heat, which causes more evaporation, which traps more heat, and so on. Under normal circumstances, Earth's climate system has ways to regulate this process and maintain stability. But there are limits to this regulation, and the slowly brightening sun will eventually push us past those limits. The process unfolds like this. As solar luminosity increases over hundreds of millions of years, global temperatures begin to rise. Initially, Earth's natural climate regulation systems can compensate. More water evaporates, but more water also condenses and falls as precipitation. More heat gets trapped by water vapor, but more heat also gets radiated away as the planet warms. The system finds a new equilibrium at a slightly higher temperature, just as it has done countless times throughout Earth's history in response to volcanic eruptions, asteroid impacts, and other climate disruptions. But as the sun continues to brighten, this delicate balance becomes increasingly difficult to maintain. Eventually, a threshold is crossed. Scientists call this the moist greenhouse limit, and it represents a point of no return for planetary habitability. Once this threshold is passed, the feedback loop between temperature and water vapor becomes unstoppable. The atmosphere fills with steam. The upper layers of the atmosphere, which normally contain very little water vapor, become saturated with moisture. And here's where the story takes a turn that leads inevitably toward empty oceans and airless skies. In the upper atmosphere, water molecules encounter high-energy ultraviolet radiation from the sun. This radiation is intense enough to break the molecular bonds that hold water together, splitting each H2O molecule into hydrogen and oxygen atoms. The oxygen is heavy enough to stay gravitationally bound to Earth, but hydrogen is the lightest element in the universe. Once freed from its molecular bonds, hydrogen atoms in the upper atmosphere can gain enough velocity to escape Earth's gravity entirely, streaming away into space like an invisible wind. This is how Earth will lose its oceans, not through boiling or evaporation in the conventional sense, but through the gradual dissociation of water molecules in the upper atmosphere and the subsequent escape of hydrogen to space. It's a process that operates on geological timescales, taking millions or tens of millions of years to complete. But it's also irreversible. Once the hydrogen is gone, it's gone forever. There's no mechanism by which a planet can recapture hydrogen that has escaped to space. As the oceans shrink, the process accelerates. Less water means less heat capacity in the climate system, so temperatures rise more quickly in response to the continued solar brightening. More water vapor reaches the upper atmosphere, where it can be broken apart by ultraviolet radiation. The hydrogen escape rate increases, and the planet enters a runaway greenhouse phase that transforms Earth from a water world into something resembling present-day Venus. This is the true story of Earth's ending. Long before the sun grows large enough to threaten our planet physically, long before any possibility of engulfment or collision, the slowly increasing solar luminosity will have transformed our blue marble into a dry, airless rock, orbiting a star that has become too bright for liquid water to exist anywhere in the solar system's habitable zone. The atmosphere will have thinned and then disappeared entirely. The oceans will have boiled away into space. The intricate web of geological processes that depend on water, from plate tectonics to weathering, will have ground to a halt. What remains will be a planet in name only, a spherical mass of rock and metal, devoid of the dynamic processes that once made it a world. This is how Earth's story ends, not with fire, but with the gradual removal of everything that made it home. The story of Earth's future might seem like pure speculation, a theoretical exercise in applying physics to imagined scenarios billions of years in the future. But the remarkable truth is that we don't have to rely on speculation alone. Across the galaxy, scattered among the hundreds of billions of stars that make up the Milky Way, astronomers have discovered evidence of what happens when stars age and planets die. We can see the aftermath of stellar evolution played out in real time, and what we see confirms our theoretical understanding of how planetary systems meet their end. The evidence comes from an unexpected source. White dwarf stars, the dense remnants left behind when sun-like stars exhaust their nuclear fuel and shed their outer layers, tell a story written in light and chemistry. These stellar corpses, each about the size of Earth but containing roughly the mass of our Sun, should be pristine objects composed almost entirely of carbon and oxygen. Their surfaces should show only the lightest elements, hydrogen and helium, because anything heavier would sink beneath the surface under the intense gravitational pull that compresses a star's worth of material into a planet-sized sphere. But that's not what we observe. When astronomers point their telescopes at white dwarf stars and analyze the light coming from their surfaces, they find something unexpected. Heavy elements, metals, silicon, iron, magnesium, calcium, and other elements that have no business being on the surface of a white dwarf star unless they arrived there recently. These polluted white dwarfs, as astronomers call them, tell the story of worlds that once were. The heavy elements we detect on white dwarf surfaces are the signatures of rocky planets and asteroids that have been torn apart by tidal forces as they spiraled too close to their parent star. Imagine a world not unlike Earth, orbiting a star not unlike our Sun. As that star ages and evolves through its red giant phase, the planet's orbit becomes unstable. Perhaps the star's mass loss causes the orbit to decay. Perhaps tidal interactions gradually drag the world inward. Eventually, the planet crosses a boundary called the Roche limit, the distance at which tidal forces from the star become stronger than the gravitational forces holding the planet together. What happens next is both violent and strangely beautiful. The planet begins to stretch, pulled into an elongated shape by the difference in gravitational force between its near side and far side. Mountains flow like water. Continents crack and separate. The world becomes a streaming river of rock and metal, forming a debris ring around its dying star. This ring of planetary material gradually spirals inward, raining down onto the white dwarf's surface and contaminating its pristine atmosphere with the heavy elements that once formed continents and ocean floors. We've catalogued thousands of these polluted white dwarfs, each one representing a planetary system that has been consumed by stellar evolution. But even more remarkably, we've begun to catch this process in the act. In 2019, astronomers using the Transiting Exoplanet Survey satellite detected something unprecedented: a white dwarf star undergoing regular dimming events every 4.5 hours. The star, catalogued as WD 1563 plus 645, showed the unmistakable signature of debris clouds passing in front of it, material from a disintegrating planet creating eclipses as it orbited the stellar remnant. This was the first direct observation of a planet in its death throes, actively being torn apart and consumed by its evolved parent star. The debris clouds contained the chemical fingerprints of what had once been a world: silicon and oxygen and metals that had perhaps once formed the bedrock of continents on a planet that might have harboured oceans, weather, maybe even life. Now reduced to clouds of dust and gas spiralling toward oblivion. But the evidence goes deeper than individual systems. Astronomers estimate that between 20 and 50% of all white dwarf stars show signs of heavy element pollution, suggesting that planetary destruction during stellar evolution is not a rare catastrophe, but a common outcome. The galaxy is littered with the remains of worlds that didn't survive their parent star's transformation from main sequence objects to white dwarfs. We've also found debris disks around white dwarfs, vast rings of pulverized planetary material that can persist for millions of years as the remnants of shattered worlds gradually rain down onto the stellar surface. These disks glow with infrared radiation as the debris absorbs starlight and re-emits it as heat, creating a ghostly signature of planetary destruction visible to our telescopes across interstellar distances. Some of these debris disks show structure, gaps and clumps that suggest the presence of surviving planetary fragments, perhaps asteroid-sized chunks of what were once entire worlds. In a few cases, astronomers have detected what appear to be the cores of former planets, dense metallic objects that survived the tidal disruption of their parent bodies and now orbit as bizarre, ultra-dense companions to white dwarf stars. The implications of these discoveries extend far beyond our own solar system. They reveal stellar evolution as a galaxy-wide process of planetary destruction and renewal. Every sun-like star will eventually become a white dwarf. Every planetary system orbiting such a star will face the same fundamental challenge: survival through a period of dramatic stellar change that transforms a stable, life-giving sun into something alien and hostile. Our solar system is not unique. The fate that awaits Earth and its neighbouring planets is playing out around countless other stars throughout the Milky Way. The difference is that most of those other planetary systems have already experienced their transformation. We're observing the aftermath, the debris fields and polluted stellar atmospheres that mark where worlds once orbited and thrived. This is perhaps the most sobering aspect of the astronomical evidence. The destruction of planetary systems by stellar evolution isn't a distant theoretical possibility. It's a process we can observe happening right now, scattered across the galaxy like crime scenes preserved in starlight. The white dwarfs polluted with heavy elements are tombstones marking the graves of worlds. And someday, billions of years from now, our own sun will join their ranks, its surface contaminated with the remains of Mercury, Venus, Earth, and Mars. To understand how the sun will eventually destroy the Earth, you first need to understand what a star really is. Not the romantic notion of a twinkling light in the darkness, not the mythological fire chariot crossing the sky, but the physical reality of what happens when gravity and nuclear physics engage in a cosmic tug-of-war that lasts for billions of years. The sun is not burning in the way that wood burns in a fireplace or gasoline burns in an engine. There is no chemical combustion happening in the solar core, no oxygen-feeding flames, no fuel being consumed in the conventional sense. Instead, the sun is powered by something far more fundamental and far more powerful: nuclear fusion. The process by which the universe creates energy by transforming matter itself, converting the lightest element into something heavier and releasing tremendous amounts of energy in the process. At the heart of our star, buried beneath 700,000 kilometers of roiling plasma, lies a core roughly the size of Jupiter, but containing nearly half the Sun's total mass. Here, under conditions so extreme they dwarf anything we can create on Earth, hydrogen nuclei are forced together against the fundamental electromagnetic forces that normally keep atomic particles apart. The temperature reaches 15 million degrees Celsius. The pressure exceeds 250 billion times Earth's atmospheric pressure at sea level. Under these conditions, the normal rules of chemistry cease to apply and nuclear physics takes over. 4 hydrogen nuclei, each containing a single proton, are fused together to create one helium nucleus, containing 2 protons and 2 neutrons. The helium nucleus weighs slightly less than the 4 individual hydrogen nuclei that created it, and that missing mass, less than 1% of the original material, is converted directly into energy according to Einstein's equation, E equals mc squared. A small amount of mass multiplied by the speed of light squared yields an enormous amount of energy. This is the engine that powers the sun. Every second, the solar core converts approximately 600 million tons of hydrogen into helium, and in the process, 4 million tons of matter are converted directly into pure energy. That energy begins as high-energy gamma rays produced by the fusion reactions, but it doesn't simply stream outward from the core to space. Instead, it begins a journey that can take anywhere from thousands to hundreds of thousands of years to complete. The sun is opaque to its own radiation. The gamma rays produced in the core are immediately absorbed by the surrounding plasma, heating it and causing it to emit new photons at slightly longer wavelengths. These photons are absorbed and re-emitted again and again, each interaction changing their energy and direction in a random walk that eventually carries the energy outward from the core toward the surface. By the time this energy finally reaches the sun's visible surface and escapes into space, it has been transformed from high-energy gamma radiation into the familiar mixture of visible light and heat that warms our planet. This process creates a delicate balance that has remained stable for 4.5 billion years. Gravity constantly tries to compress the sun, pulling all that solar material inward toward the center. But the energy generated by nuclear fusion creates an outward pressure that exactly counteracts gravity's inward pull. The sun maintains its size and shape because these two forces are perfectly balanced. Gravity prevents the sun from flying apart. Fusion pressure prevents the sun from collapsing. The result is a stable star that can maintain this equilibrium for billions of years. But stability doesn't mean unchanging. Even though the sun appears constant from our perspective, it's actually undergoing continuous, gradual evolution. The fusion process that powers our star is slowly but inexorably changing the composition of the solar core. Every time 4 hydrogen nuclei fuse to create one helium nucleus, the core becomes slightly more dominated by helium and slightly less dominated by hydrogen. Over millions and billions of years, this accumulation of helium ash alters the fundamental properties of the stellar core. Helium nuclei are heavier than hydrogen nuclei and behave differently under the extreme conditions of stellar fusion. As the core's helium content increases, the nuclear physics of the fusion process begins to change. The core must become slightly hotter and slightly denser to maintain the same rate of energy production. These changes ripple outward through the star's interior, affecting the balance between gravity and radiation pressure that keeps the sun stable. The result is a gradual increase in the sun's luminosity. As the core becomes more efficient at fusion, due to its changing composition, more energy is produced, and more energy eventually makes its way to the surface and radiates into space. This increase is slow by human standards, roughly 10% per billion years, but it's relentless and unstoppable as long as hydrogen fusion continues in the core. This is why the sun that shone on the early Earth 4 billion years ago was noticeably dimmer than the sun that shines today, and why the sun that will shine on Earth in the future will be noticeably brighter than today's sun. The same nuclear process that gives us life contains within it the mechanism of Earth's eventual destruction. The gradual brightening is not a malfunction or an accident. It's the inevitable result of hydrogen fusion proceeding exactly as physics dictates it must. The Sun is currently what astronomers classify as a main sequence star, meaning it's in the stable, hydrogen-burning phase of its evolution. This phase represents the longest and most stable period of a star's life, when the balance between gravity and fusion pressure can be maintained with relatively minor adjustments. Our Sun has been a main sequence star for 4.5 billion years, and it will remain one for roughly another 5 billion years. But even during this stable phase, the slow brightening continues, and the consequences for planetary habitability accumulate over geological time. Understanding this process, this gradual evolution of stellar properties driven by nuclear physics, is the key to understanding Earth's ultimate fate. The Sun isn't going to suddenly explode or dramatically change overnight. Instead, it will continue its slow, steady march toward higher luminosity, eventually pushing our planet past the thresholds that make liquid water, breathable atmospheres, and ultimately life itself possible. The story of the Sun's betrayal unfolds not in dramatic moments, but in increments so small they're imperceptible to human experience. Each year, the Sun becomes slightly brighter than it was the year before. Each century adds a barely measurable increase to the total energy streaming toward Earth. Each millennium brings our planet closer to thresholds that will transform everything we know about habitability. This is the slow brightening, a subtle betrayal by the very star that gave us life. To understand just how gradual this process is, consider that the Sun has brightened by roughly 25 to 30% since Earth first formed 4.5 billion years ago. That sounds significant until you realize it represents an average increase of less than 7% per billion years. In human terms, this is essentially imperceptible. The difference in solar brightness between your birth and your death amounts to a change measured in parts per billion. Your children and grandchildren and their grandchildren for thousands of generations will see essentially the same Sun you see today. But geology operates on different timescales than human experience, and climate systems integrate changes over periods that dwarf the entirety of recorded history. A few percent increase in solar energy input, accumulated over millions of years, is enough to shift ice ages, alter ocean circulation patterns, and push ecosystems past tipping points. 30% more energy, accumulated over billions of years, is enough to transform Earth from the blue marble we know today into something unrecognizable. The physics behind this brightening is deceptively simple. As we've seen, the Sun's core gradually becomes more dominated by helium as hydrogen fusion proceeds. Helium nuclei are more massive than hydrogen nuclei, so the core becomes denser over time. A denser core can sustain fusion reactions at a higher rate, generating more energy per unit time. Additionally, the accumulation of helium ash changes the core's thermal properties, requiring slightly higher temperatures to maintain pressure balance against gravity. Higher core temperatures drive faster fusion rates, which produce more energy, which must eventually make its way to the surface and radiate into space. The result is a feedback loop, though a very slow one. More helium leads to higher core density and temperature. Higher core temperature leads to faster fusion rates. Faster fusion produces more energy and creates more helium. The process is self-reinforcing, though it proceeds gradually enough that the Sun can maintain overall stability for billions of years while slowly but steadily increasing its energy output. From Earth's perspective, this gradual brightening creates a moving target for planetary habitability. The conditions that make our world suitable for liquid water and complex chemistry are not fixed in time. They exist within a narrow range of solar energy input, and as that input slowly increases, Earth's climate system must continuously adapt to maintain the delicate balance that keeps our oceans liquid and our atmosphere breathable. For most of Earth's history, this adaptation has been successful. Despite the Sun being significantly dimmer in the past, geological evidence shows that liquid water has existed on Earth's surface for at least 3.5 billion years, possibly longer. This apparent contradiction, known as the faint young sun paradox, initially puzzled astronomers and climate scientists. How could early Earth maintain liquid oceans under a sun that was 20 to 25% dimmer than today? The answer lies in Earth's atmosphere and its remarkable ability to regulate planetary temperature through the greenhouse effect. In the early solar system, Earth's atmosphere contained much higher concentrations of greenhouse gases, particularly carbon dioxide, than it does today. These gases trapped heat more effectively, compensating for the dimmer sun and keeping global temperatures warm enough for liquid water. As the sun gradually brightened over geological time, atmospheric greenhouse gas concentrations slowly declined, maintaining a roughly stable global temperature despite the increasing solar energy input. This atmospheric regulation isn't random or accidental. It's driven by a complex network of geological processes that form what scientists call the carbonate-silicate cycle, a planetary thermostat that automatically adjusts atmospheric carbon dioxide levels in response to changing conditions. When temperatures rise, chemical weathering of rocks increases, pulling more carbon dioxide out of the atmosphere and storing it in carbonate minerals. When temperatures fall, volcanic outgassing and reduced weathering allow carbon dioxide levels to rise, trapping more heat. This system has kept Earth's climate remarkably stable despite dramatic changes in solar luminosity, atmospheric composition, and continental configuration over billions of years. But even the most sophisticated thermostat has limits. As the sun continues to brighten, the carbonate-silicate cycle will eventually reach a point where it can no longer compensate for the increasing energy input. The system that has maintained Earth's habitability for billions of years will begin to break down, not because it's malfunctioning, but because it's being asked to regulate conditions beyond its operational range. Climate models suggest this breakdown will begin within the next billion years, possibly sooner. Solar luminosity increases beyond a certain threshold. The amount of carbon dioxide that must be removed from the atmosphere to maintain stable temperatures drops below the minimum needed to support the geological processes that drive the carbonate-silicate cycle. The planetary thermostat begins to fail, temperatures start to rise unchecked, and Earth enters the runaway greenhouse phase that will eventually strip away its oceans and atmosphere. This is the subtle treachery of stellar evolution. The same nuclear processes that have powered 4 billion years of terrestrial evolution carry within them the seeds of the planet's ultimate uninhabitability. The sun's gradual brightening is not a malfunction to be corrected or a catastrophe to be avoided. It's the inevitable consequence of physics operating exactly as it should, transforming our life-giving star into something that no planet in the solar system can survive. The betrayal is made more poignant by its gentleness. There will be no dramatic moment when the sun suddenly becomes hostile to life. Instead, there will be a gradual crossing of thresholds, each one imperceptible in human terms, but decisive in planetary terms. First, the failure of climate regulation, then the beginning of atmospheric escape, then the slow evaporation of the oceans, each step following naturally from the previous one in a sequence as predictable as sunrise. For 4.5 billion years, Earth has maintained liquid water on its surface, despite dramatic changes in solar luminosity, atmospheric composition, and continental configuration. This remarkable stability isn't accidental or miraculous. It's the result of a sophisticated planetary thermostat that automatically adjusts atmospheric conditions to compensate for changing energy inputs. Understanding how this thermostat works and why it will eventually fail is crucial to understanding Earth's ultimate fate under an ever-brightening sun. The thermostat is called the carbonate-silicate cycle, and it operates through a complex network of geological processes that regulate the amount of carbon dioxide in Earth's atmosphere. Carbon dioxide is a greenhouse gas, meaning it traps heat and warms the planet's surface. The more carbon dioxide in the atmosphere, the warmer Earth becomes. The less carbon dioxide, the cooler the planet gets. This relationship between atmospheric carbon dioxide and global temperature forms the basis of Earth's climate regulation system. The cycle begins with carbon dioxide dissolving in rainwater to form weak carbonic acid. When this slightly acidic water comes into contact with silicate rocks, particularly those containing calcium and magnesium, a chemical reaction occurs that breaks down the rock minerals and combines the dissolved ions with atmospheric carbon dioxide to form bicarbonate compounds. These compounds eventually make their way to the oceans through rivers and groundwater, where marine organisms use them to build calcium, carbonate shells and skeletons. When these organisms die, their calcium carbonate remains settled to the ocean floor, forming limestone and other carbonate sediments. Over geological time, these sediments are buried, compressed, and eventually subducted beneath continental plates through the process of plate tectonics. Deep in the Earth's mantle, the high temperatures and pressures break down the carbonate minerals, releasing carbon dioxide that eventually returns to the atmosphere through volcanic eruptions. The cycle is complete. This might seem like a simple chemical process, but it functions as a remarkably sensitive climate control system. When global temperatures rise, several things happen that increase the rate at which carbon dioxide is removed from the atmosphere. Higher temperatures accelerate chemical weathering reactions, causing rocks to break down faster and consume more atmospheric carbon dioxide in the process. Increased temperatures also drive more vigorous hydrological cycles, with more evaporation, more precipitation, and more flowing water to carry the chemical weathering products to the oceans. Conversely, when global temperatures fall, chemical weathering slows down, less carbon dioxide is removed from the atmosphere, and volcanic outgassing gradually increases atmospheric carbon dioxide levels. Higher carbon dioxide concentrations trap more heat, warming the planet back toward equilibrium. It's a negative feedback system, one that automatically opposes changes in global temperature by adjusting the very atmospheric component that controls how much solar energy Earth retains. The power of this system is evident throughout Earth's geological history. When the Sun was 25% dimmer than today, higher atmospheric carbon dioxide levels compensated for the reduced solar energy input, keeping Earth warm enough for liquid water and early life. As the Sun gradually brightened over billions of years, the carbonate-silicate cycle slowly reduced atmospheric carbon dioxide concentrations, maintaining relatively stable global temperatures despite the increasing energy input from space. The system has weathered extraordinary perturbations. Massive volcanic eruptions that injected enormous amounts of carbon dioxide into the atmosphere have been gradually balanced by increased chemical weathering. Asteroid impacts that dramatically altered atmospheric composition have been followed by slow returns to equilibrium. Ice ages and warm periods have come and gone, but through it all, the carbonate-silicate cycle has maintained conditions suitable for liquid water on Earth's surface. But like any regulatory system, Earth's thermostat has operational limits. The cycle depends on having enough atmospheric carbon dioxide to support the chemical reactions that drive rock weathering, and it depends on geological processes like plate tectonics and volcanism to complete the carbon cycle between atmosphere, oceans, and deep Earth. As the sun continues to brighten and more carbon dioxide must be removed to maintain stable temperatures, the system approaches thresholds beyond which it cannot function effectively. Climate models suggest that within the next billion years, possibly sooner, the amount of carbon dioxide that must be removed from Earth's atmosphere to compensate for increased solar energy will drop below the minimum levels needed to support robust chemical weathering and biological processes. When atmospheric carbon dioxide concentrations fall too low, plants can no longer photosynthesize effectively, ecosystems collapse, and the weathering reactions that remove carbon dioxide from the atmosphere slow dramatically. This creates a tipping point. Once the carbonate-silicate cycle begins to fail, there's no mechanism to prevent atmospheric carbon dioxide levels from continuing to decline. Without adequate greenhouse warming to counteract the sun's increasing brightness, Earth's surface temperature begins to rise unchecked. The planet enters what scientists call a runaway greenhouse state, where increasing temperatures drive more water vapor into the atmosphere, and water vapor, being itself a powerful greenhouse gas, causes even more warming. The failure of Earth's thermostat represents one of the most profound transitions in our planet's history. For billions of years, geological processes have maintained the delicate balance of atmospheric chemistry that makes life possible. The same processes that built the oxygen-rich atmosphere we breathe, that regulated carbon dioxide levels through ice ages and warm periods, that allowed complex life to evolve and thrive, will eventually prove inadequate to cope with an ever-brightening sun. What makes this transition particularly sobering is its inevitability. The carbonate-silicate cycle isn't breaking down due to external catastrophe or system failure. It's reaching the natural limits of its regulatory capacity, pushed beyond its operational range by the slow but relentless increase in solar energy output. The thermostat that has kept Earth habitable for longer than life has existed on land will simply run out of room to turn down. This is the true meaning of the sun's slow brightening. It's not just about rising temperatures or changing weather patterns. It's about the fundamental breakdown of the planetary systems that have maintained Earth as a living world for billions of years, systems whose limits are not infinite, whose remarkable stability will eventually give way to transformation beyond anything our planet has ever experienced. The first ending of Earth as a habitable world won't come with fire or ice or any of the dramatic catastrophes that capture human imagination. It will come when water, the most essential ingredient for life as we know it, simply stops being stable on our planet's surface. This transition marks a threshold more fundamental than any in Earth's history, the moment when the basic physics of our world shift beyond the boundaries that have defined habitability for billions of years. Water exists in three phases: solid, liquid, and gas, and the boundaries between these phases depend critically on temperature and pressure. On Earth today, water is stable as a liquid across most of the planet's surface because our global temperature falls within the narrow range where H2O molecules move fast enough to remain fluid, but not so fast that they escape into the atmosphere as vapor. This liquid stability zone has been Earth's defining characteristic since the earliest days of our planet's history, enabling everything from the first primitive cells to the complex ecosystems that surround us today. But as the sun's luminosity increases, this stability zone begins to shrink. The process doesn't happen overnight or even over human timescales. Instead, it unfolds over hundreds of millions of years, as slowly rising temperatures gradually shift the balance between water's liquid and vapor phases. Initially, the changes are subtle. More evaporation from oceans and lakes, slightly higher humidity, increased cloud cover that initially provides some cooling through reflection of sunlight back to space. These early changes might even seem beneficial from a human perspective. More water vapor in the atmosphere means more frequent rainfall in some regions, potentially supporting more lush vegetation and expanded habitable zones. The increased cloud cover helps moderate temperature increases, acting as a natural air conditioning system that partially offsets the sun's increasing energy output. For millions of years, Earth's climate system adapts and adjusts, finding new equilibrium points that maintain overall habitability despite the changing energy inputs. But water vapor is itself a greenhouse gas, and a particularly powerful one. Unlike carbon dioxide, which makes up a tiny fraction of our atmosphere, water vapor can constitute several percent of the air we breathe, and its greenhouse effect is correspondingly stronger. As temperatures rise and more water evaporates, this additional water vapor traps more heat, causing more evaporation, which traps more heat, creating what scientists call a positive feedback loop. Unlike the negative feedback of the carbonate-silicate cycle that tends to stabilize Earth's climate, this water vapor feedback amplifies changes rather than dampening them. Small increases in temperature lead to larger increases in atmospheric water vapor, which cause larger increases in trapped heat, which drive even more evaporation. The system becomes self-reinforcing, and once it begins, there's no natural mechanism to stop it. The critical transition occurs when this feedback loop overwhelms Earth's ability to radiate excess heat back to space. Every object, including planets, emits thermal radiation in proportion to its temperature. As Earth warms, it radiates more energy, which normally helps restore balance by carrying away the excess heat from increased solar input. But when atmospheric water vapor concentrations become high enough, this outgoing radiation gets trapped more efficiently than the additional energy can be radiated away. Scientists call this threshold the moist greenhouse limit, and it represents a point of no return for planetary habitability. Once crossed, Earth's surface temperature begins to climb in a runaway process that continues until all liquid water has boiled away. The planet doesn't need to reach the boiling point of water at sea level, 100 degrees Celsius. Long before temperatures climb that high, the increasing water vapor content of the atmosphere will have initiated the runaway greenhouse effect that makes liquid water permanently unstable. The process that follows is both elegant and terrifying in its inexorability. As surface temperatures climb, more water evaporates from the oceans. The atmospheric water vapor concentration increases, reaching levels far higher than anything in Earth's current climate system. The upper atmosphere, which today contains almost no water vapor, becomes saturated with moisture. And here, in the thin air 60 to 80 kilometers above the surface, solar ultraviolet radiation begins to play its destructive role. Water molecules in the upper atmosphere encounter high-energy ultraviolet photons from the sun. These photons carry enough energy to break the chemical bonds that hold water molecules together, splitting each H2O molecule into 2 hydrogen atoms and 1 oxygen atom. The oxygen atoms eventually combine to form molecular oxygen or other oxygen compounds that remain gravitationally bound to Earth. But hydrogen, the lightest element in the universe, behaves differently. At the temperatures and low densities of the upper atmosphere, hydrogen atoms can achieve velocities that exceed Earth's escape velocity of 11.2 kilometers per second. Once they reach these velocities, they are no longer bound by Earth's gravity and stream away into space like an invisible wind. This is how Earth will lose its oceans, not through boiling in the conventional sense, but through the gradual dissociation of water molecules in the upper atmosphere and the subsequent escape of hydrogen to space. The process operates on geological timescales, taking millions or tens of millions of years to strip away the equivalent of Earth's current oceans. But it's also irreversible. Once hydrogen escapes to space, there's no mechanism by which a planet can recapture it. The water that took billions of years to accumulate through volcanic outgassing and comet impacts will be lost forever, leaving behind only the oxygen that was too heavy to escape. As the oceans shrink, the process accelerates. Less water means less heat capacity in the climate system, so temperatures rise more quickly in response to the continued solar brightening. More water vapor reaches the upper atmosphere, where it can be broken apart by ultraviolet radiation. The rate of hydrogen escape increases, and Earth enters the final phase of its transformation from a water world into something resembling Venus, hot, dry, and utterly hostile to life. This is the first ending, the moment when 4 billion years of liquid water stability comes to a close. Long before the Sun grows large enough to physically threaten Earth, long before any possibility of planetary engulfment, the slowly increasing solar luminosity will have made liquid water impossible on our planet's surface. The blue marble will become a red one, and the story of life on Earth will enter its final chapter. When confronting the ultimate fate of our planet, it's natural to want precise dates, exact timelines, definitive answers about when these cosmic transformations will unfold. But the universe operates with a complexity that resists simple schedules, and the story of Earth's future requires us to embrace both certainty and uncertainty with equal measure. We can be confident about the fundamental processes that will reshape our world, while acknowledging that the precise timing depends on variables we're still working to understand. The mainstream scientific consensus, built from decades of stellar evolution modeling and climate system analysis, provides us with a framework for understanding when Earth's habitability will face its greatest challenges. Current models consistently suggest that the moist greenhouse threshold, the point at which Earth's climate system begins its irreversible transition toward a Venus-like state, will be crossed within the next 1 to 2 billion years. Some studies place this transition as early as 600 million years from now. Others suggest it might not occur for 1.5 billion years, but virtually all agree that it will happen within this broad time frame. These differences in timing aren't the result of scientific disagreement about fundamental physics, but rather reflect the extraordinary complexity of modeling systems that operate over geological timescales. Climate scientists must account not only for the Sun's gradually increasing luminosity, but also for changes in Earth's orbital parameters, variations in atmospheric composition, the evolution of continental configurations through plate tectonics, and feedback loops between the atmosphere, oceans, and biosphere that we're still working to fully understand. The uncertainties become even more pronounced when we move beyond the moist greenhouse transition to consider the Sun's later evolutionary phases. Astrophysical models consistently predict that the Sun will begin its transformation into a red giant star in approximately 5 billion years. But the exact timeline and characteristics of this transformation depend on detailed properties of stellar structure that remain challenging to model with perfect precision. Small differences in the Sun's internal composition, rotation rate, or magnetic field evolution can translate into variations of hundreds of millions of years in the timing of specific evolutionary phases. What we can say with confidence is that the sequence of events is well understood, even if the precise scheduling remains uncertain. The Sun will continue to brighten as helium accumulates in its core. Earth's climate regulation systems will eventually be overwhelmed by this increasing energy input. The planet will transition into a runaway greenhouse state that strips away its oceans and atmosphere. Later, much later, the Sun will exhaust the hydrogen fuel in its core and begin the dramatic expansion that transforms it from a main sequence star into a red giant. Each of these transitions follows from well-established physical principles observed in countless other stellar systems throughout the galaxy. Perhaps more important than the exact timing is the scale of these changes relative to human experience and even to the history of life on Earth. 1 billion years is a span of time that dwarfs every familiar reference point. It's twice as long as complex multicellular life has existed on our planet. It's 200 times longer than the entire history of flowering plants. It's 5,000 times longer than all of recorded human history. Even the most conservative estimates place Earth's transition to uninhabitability so far in the future that the very concept of time begins to lose meaning in human terms. To put this in perspective, if Earth's entire 4.5 billion year history were compressed into a single year, with the planet's formation occurring on January 1st, the first simple cells would appear in early March. Complex cells wouldn't evolve until late August, and multicellular life wouldn't emerge until mid-November. Dinosaurs would appear on December 13th and disappear on December 26th. All of human history would occupy the final few minutes before midnight on December 31st. The moist greenhouse transition, even in the most pessimistic scenarios, wouldn't occur until sometime in the following March. This vast temporal cushion doesn't diminish the significance of understanding Earth's ultimate fate, but it does provide context for contemplating these cosmic changes without despair. The processes that will eventually make our planet uninhabitable are the same processes that have sustained life for billions of years. The Sun's nuclear fusion, which will eventually doom Earth's habitability, has provided the stable energy source that enabled the evolution of everything from bacteria to blue whales. The geological cycles that will fail to regulate our future climate have maintained conditions suitable for liquid water longer than life has existed on land. Moreover, the timescales involved offer profound perspective on humanity's place in the cosmic story. If current trends in technological development continue for even a tiny fraction of the time remaining before Earth becomes uninhabitable, our species and our descendants will have capabilities that are literally unimaginable today. The difference between our current technology and what might be possible in 1 billion years is far greater than the difference between a stone axe and a spacecraft. Any discussion of humanity's ultimate survival must acknowledge that the beings who face Earth's final challenges will be as different from us as we are from the earliest life forms. The uncertainties in timing also reflect something profound about the nature of scientific understanding. We can predict with confidence that the sun will brighten, that Earth's climate will eventually be overwhelmed, and that our planet will lose its habitability long before being physically destroyed. These predictions emerge from fundamental physics that we understand well and have tested extensively. But the precise details of how these processes unfold depend on complex interactions between systems operating over timescales far longer than human civilization has existed. This is not a failure of science, but rather a testament to the extraordinary complexity of the systems we're attempting to understand. The fact that we can predict the general course of Earth's future evolution at all, despite operating with incomplete information over timescales measured in billions of years, represents one of the greatest intellectual achievements in human history. We are, quite literally, using the light from distant stars and the mathematics of nuclear physics to peer billions of years into our planet's future. The timeline may be uncertain in its details, but the destination is clear. Earth's time as a habitable world is finite, measured against the vast scales of cosmic evolution. Understanding this timeline without panic or despair requires us to hold both the certainty of physical law and the uncertainty of complex systems in proper perspective. The transformation of the Sun from the stable, life-giving star we know today into something alien and hostile begins with a crisis at its very heart. For billions of years, the solar core has been the ultimate example of cosmic stability, a fusion reactor operating under such perfectly balanced conditions that its energy output has varied by less than a few percent over the entire history of complex life on Earth. But this stability, impressive as it is, cannot last forever. Eventually, inevitably, the core will begin to run short of the fuel that has powered it for nearly 5 billion years. The crisis doesn't announce itself with dramatic changes visible from Earth. There are no sudden flickers in the sun's brightness, no obvious alterations in the quality of sunlight streaming toward our planet. Instead, the transition begins deep within the solar interior, in a region smaller than Jupiter but containing roughly half the sun's total mass, where temperatures reach 15 million degrees Celsius, and the pressure exceeds 200 billion times Earth's atmospheric pressure at sea level. Here, in this cosmic furnace, hydrogen nuclei have been fusing into helium for so long that the fundamental chemistry of stellar fusion is beginning to change. The core, which started its life as nearly pure hydrogen, has gradually become a mixture of hydrogen and helium, with the helium fraction growing larger each passing year. This might seem like a minor compositional change, but in the extreme environment of a stellar core, small differences in nuclear composition translate into large differences in how fusion reactions proceed. Helium nuclei are heavier than hydrogen nuclei and more difficult to fuse together. They require higher temperatures and pressures to overcome the electromagnetic forces that keep atomic particles apart. As the core becomes more dominated by helium, the nuclear reactions that power the Sun become increasingly concentrated in a shell surrounding the helium-rich center, rather than throughout the entire core volume. This shell burning is less stable than the distributed core burning that has characterized the Sun's main sequence lifetime, and it marks the beginning of the end of our star's long period of steady, reliable energy production. The transition from core hydrogen fusion to shell hydrogen fusion represents one of the most fundamental changes a star can undergo. It's the stellar equivalent of a heart transplant, except that instead of receiving a new heart, the star must learn to live with a completely different circulatory system. The new configuration is inherently unstable, prone to fluctuations in energy production that will eventually grow large enough to reshape the entire structure of the star. As hydrogen becomes scarce in the central core, the nuclear reactions that generate the outward pressure needed to balance gravity's inward pull begin to weaken in that region. Without sufficient radiation pressure to support it against gravitational collapse, the helium-rich core starts to contract. This contraction releases gravitational potential energy, heating the core and the surrounding hydrogen-rich material. Paradoxically, as the core contracts and the Sun begins its transition away from main sequence stability, the star actually becomes more luminous, not less. The physics behind this counterintuitive behavior reveals one of the most elegant principles of stellar evolution. When the heart of a star contracts, the rest of the star responds by expanding. As the core shrinks and heats up, the hydrogen shell surrounding it burns more vigorously, producing more energy than the star generated during its stable main sequence phase. This excess energy travels outward through the solar interior, eventually reaching the surface and radiating into space as increased luminosity. But the energy doesn't just pass through the outer layers of the Sun unchanged. As it moves outward from the increasingly energetic shell-burning region, it encounters material that must absorb and transport this enhanced energy flow. The outer layers of the Sun, unable to radiate away all this excess energy efficiently, begin to expand and cool. The surface temperature drops, giving the star a redder appearance, while the total energy output increases dramatically. This is the birth of a red giant star, a process driven not by external catastrophe or system failure, but by the internal logic of stellar physics responding to fuel depletion in the core. The same gravitational forces that have held the Sun together for billions of years now drive its transformation into something larger, cooler, and far more luminous than the star that nurtured the evolution of life on Earth. The transition doesn't happen overnight. Stellar evolution operates on timescales measured in millions and hundreds of millions of years, far longer than human civilization has existed, but remarkably rapid compared to the billions of years the Sun has spent as a stable main sequence star. As the core continues to contract and the shell burning becomes more intense, the outer layers expand further and further from the stellar center. The Sun will grow to many times its current radius, extending outward until it engulfs the orbits of the inner planets. Its surface will cool to temperatures lower than today's solar surface, giving it the characteristic red color that defines giant stars. But despite this cooler surface temperature, the sheer size of the expanded star means it will radiate far more total energy than the Sun produces today. From Earth's perspective, long before the Sun's physical expansion threatens our planet directly, the increased luminosity will have completed the destruction of terrestrial habitability that began billions of years earlier with the gradual brightening of the main sequence Sun. The red giant phase represents not the beginning of Earth's problems, but their dramatic culmination. This is the cosmic principle at work throughout the universe. When the heart changes, the whole body changes. The fuel shortage that begins in a region smaller than Jupiter ultimately transforms a star system spanning billions of kilometers. The same nuclear physics that sustained stable conditions for geological ages becomes the driver of change so profound that no planet in the inner solar system can survive it unchanged. The Sun's core is turning on itself, not through malice or malfunction, but through the inevitable consequences of billions of years of successful operation. The fusion reactions that gave us life contain within them the seeds of the star's own transformation, and our planet's ultimate uninhabitability is written in the same nuclear physics that powers every sunset we have ever witnessed. The story of Earth's final fate involves a cosmic irony that reveals itself only when you understand the delicate mechanics of planetary orbits around an evolving star. Common sense suggests that as the Sun grows larger and more threatening, Earth's best hope for survival would be to move farther away to somehow increase its orbital distance and escape the expanding stellar envelope. And indeed, this is exactly what will happen. Earth's orbit will drift outward as the Sun evolves. But this apparent retreat from danger masks a more complex gravitational dance, one where moving away might not be enough to ensure survival, and where the very forces that seem to offer salvation could ultimately seal our planet's doom. The orbital mechanics begin with a fundamental principle that governs all gravitational systems. The strength of gravitational attraction between two objects depends on their masses and the distance between them, but it also depends on the total amount of mass doing the attracting. As the Sun evolves from a main sequence star into a red giant, it doesn't just change size and temperature. It also loses mass, shedding material through stellar winds that carry away portions of the solar atmosphere into interplanetary space. This mass loss has immediate consequences for planetary orbits. The gravitational force that keeps Earth in its current orbit depends on the Sun's mass. As the Sun becomes less massive, its gravitational grip on the planets weakens proportionally. The result is that planetary orbits naturally expand outward, with each planet settling into a new equilibrium at a greater distance from the Sun's center. For Earth, this orbital expansion initially seems like a stroke of cosmic good fortune. As the Sun begins to swell into a red giant with a radius many times larger than today's solar diameter, Earth's orbit moves outward, potentially keeping our planet outside the expanding solar envelope. Computer simulations suggest that by the time the Sun reaches its maximum red giant size, Earth's orbit could have expanded by 10 to 20%, possibly enough to avoid direct engulfment by the stellar atmosphere. But the gravitational story doesn't end with simple orbital expansion. The Sun's evolution involves not just mass loss, but also structural changes that create new gravitational interactions between the star and its planets. As the Sun's outer layers expand and become more diffuse, they begin to interact with planetary orbits through a phenomenon called tidal friction. Tidal forces arise whenever two gravitating bodies are close enough that the gravitational field of one body is noticeably stronger on the near side of the other body than on the far side. We see tidal forces at work every day in Earth's oceans, where the Moon's gravity creates bulges of water that follow the lunar orbit and produce our familiar pattern of high and low tides. But tidal interactions also occur between planets and stars, and when a star expands to the enormous size of a red giant, these interactions become powerful enough to influence planetary orbits. The expanded Sun will raise tides on Earth far stronger than anything our planet has ever experienced. But more importantly, these tidal interactions work both ways. Just as the Sun raises tides on Earth, Earth raises tides on the Sun, creating bulges in the stellar atmosphere that are dragged along by our planet's orbital motion. This creates a form of friction between planet and star, a gravitational drag that slowly robs energy from Earth's orbit and causes the planet to spiral inward toward the stellar center. The outcome of this gravitational competition between orbital expansion due to mass loss and orbital decay due to tidal friction becomes a cosmic coin flip with Earth's survival hanging in the balance. If mass loss dominates, Earth moves outward fast enough to stay ahead of the expanding solar envelope, potentially surviving the red giant phase as a scorched but intact world. If tidal friction dominates, Earth spirals inward despite the Sun's mass loss, eventually crossing into the extended stellar atmosphere and meeting its destruction through atmospheric drag and extreme heating. Current models suggest the outcome will be very close, with Earth's fate balanced on the knife edge between survival and destruction. Small uncertainties in the rate of solar mass loss, the efficiency of tidal coupling, or the details of the Sun's structural evolution during the red giant phase could tip the balance either way. Some studies conclude that Earth will barely escape engulfment, ending up as a hot, airless rock in a wider orbit around a white dwarf star. Others predict that tidal friction will win the contest, dragging our planet into the solar atmosphere for a fiery conclusion to its 4.5 billion year history. But this focus on engulfment versus survival misses a crucial point that renders the distinction largely academic. Even in the scenarios where Earth avoids direct physical contact with the red giant Sun, our planet will have been uninhabitable for billions of years before the stellar expansion begins. The slow brightening that destroys Earth's climate and strips away its oceans and atmosphere occurs during the Sun's main sequence evolution, long before any transition to red giant status. By the time the Sun begins its dramatic expansion, Earth will already be a desiccated, airless world bearing no resemblance to the blue marble that once harboured life. Whether this dead planet survives the red giant phase intact or gets consumed by the expanding stellar envelope is a question of academic interest for cosmic archaeology, but it has no bearing on the habitability that will have ended eons earlier. The geometry of doom is thus more subtle and more comprehensive than simple engulfment scenarios suggest. Earth's fate is sealed not by the dramatic expansion of the Sun into a red giant, but by the gradual brightening that occurs billions of years earlier. The orbital mechanics that determine whether our planet avoids physical destruction become irrelevant to the question of survival, because survival in any meaningful sense will have already become impossible. This is perhaps the most haunting aspect of Earth's future. The cosmic processes that might offer our planet a narrow escape from physical annihilation will be operating on a world that has already lost everything that made it worth saving. The delicate gravitational dance between tidal friction and mass loss will play out around a planet that has become a monument to what once was, rather than a refuge for what might yet be. The red giant arrives not as a monster bursting forth from the depths of space, but as the inevitable consequence of stellar physics operating exactly as it should. There is something almost gentle about this transformation, a cosmic metamorphosis that unfolds over millions of years with the slow majesty of geological change. The sun doesn't explode into red giant status overnight. Instead, it grows, gradually and inexorably, following a script written in the fundamental laws that govern how stars live and die throughout the universe. When we speak of the sun becoming a red giant, we're describing a star that has fundamentally changed its relationship with space and energy. The familiar golden disk that has hung in Earth's sky for billions of years will be replaced by something alien yet beautiful, a vast, diffuse ember that dominates the inner solar system. To understand what this transformation means, you need to abandon your everyday intuitions about how stars work and embrace the counterintuitive physics of objects so massive that they create their own rules for existence. The sun's expansion begins in its core, as we've seen, but the effects propagate outward through the stellar interior like ripples spreading across a cosmic pond. As the core contracts under its own gravity and the hydrogen-burning shell intensifies, the increased energy output heats the overlying layers of stellar material. These outer regions, unable to radiate away the excess energy efficiently, respond by expanding outward, growing larger and more diffuse as they try to establish a new equilibrium between energy input and energy loss. But this expansion involves a trade-off that reveals one of the most elegant principles in stellar physics. As the sun's outer layers expand to a much larger radius, their surface area increases dramatically. More surface area means more space through which the star can radiate energy into space. To maintain the same total energy output through a much larger surface, each square meter of the stellar surface must radiate less energy than before, which means it must be cooler than the current solar surface. The result is a star with a surface temperature significantly lower than today's sun, perhaps 3,000 to 4,000 degrees Celsius, compared to the current solar surface temperature of nearly 6,000 degrees. This cooler surface temperature gives the star its characteristic red appearance, as the peak wavelength of its thermal radiation shifts toward the longer, redder wavelengths that our eyes perceive as red and orange light. Yet, despite this cooler surface temperature, the red giant sun will be far more luminous than today's star. The enormous increase in surface area more than compensates for the lower temperature per unit area. A red giant star might have a surface temperature only 60% of the main sequence sun's temperature, but if its radius increases by a factor of 50, its total surface area increases by a factor of 2,500. Even accounting for the reduced energy output per unit area, the total luminosity can be hundreds or even thousands of times greater than the main sequence sun. This is the central paradox of red giant stars. They appear red and relatively cool, but they pump far more total energy into space than the hot, bright stars we're accustomed to thinking of as powerful. The red giant sun will be simultaneously cooler and more energetic than any star Earth has ever known, a contradiction that makes sense only when you consider the vast scale of the stellar expansion. The numbers involved in this expansion are difficult to comprehend in everyday terms. The current sun has a radius of approximately 700,000 kilometers, large enough that more than 100 Earths could fit across its diameter. The red giant sun will expand to a radius of perhaps 50 to 100 million kilometers, large enough to engulf the entire orbit of Mercury and possibly Venus as well. If you could somehow stand on Earth's surface during this expansion, the sun would no longer appear as a disk in the sky, but as a glowing dome that covers a significant fraction of the celestial sphere. The transformation doesn't happen uniformly or predictably. Red giant evolution involves phases of rapid expansion followed by periods of relative stability, creating a complex pattern of stellar behavior that can last for hundreds of millions of years. The star may pulsate, growing and shrinking in regular cycles as its structure adjusts to the changing energy production in its interior. It may shed mass through stellar winds that carry away portions of the solar atmosphere, creating beautiful but ephemeral structures in the space around the dying star. These stellar winds represent another aspect of red giant evolution that has profound implications for planetary systems. Unlike the relatively gentle solar wind that streams away from today's sun, carrying away tiny amounts of solar material, red giant winds can remove substantial fractions of a star's total mass. The red giant sun may lose 20 to 30% of its current mass through these winds, material that once formed part of the stellar core and atmosphere, but now drifts away into interstellar space. For any planets that might survive to witness this transformation, the red giant phase represents a complete restructuring of their cosmic environment. The intense radiation from the enormously luminous star will strip away any remaining atmospheres and bake planetary surfaces to temperatures that make Venus seem cool by comparison. The stellar winds will create a tenuous but persistent flow of hot plasma throughout the inner solar system, gradually eroding any solid objects that remain in the path of this stellar exhalation. The expansion also changes the gravitational landscape of the solar system in subtle but important ways. As the Sun's mass decreases due to stellar winds, planetary orbits naturally expand outward, as we've discussed, but the red giant's enormous size creates new gravitational interactions that can destabilize orbits that have remained stable for billions of years. Planets that survive the initial phases of red giant evolution may find themselves in increasingly eccentric orbits, subject to extreme variations in stellar heating as they swing closer to and farther from the evolved Sun. Through all of this transformation, there is a strange beauty in the physics at work. The same nuclear processes that powered billions of years of stable solar evolution now drive a spectacular finale that will reshape the entire solar system. The red giant sun will be a fundamentally different kind of star than the one that nurtured the development of life on Earth. But it will still be our sun, following the same physical laws, obeying the same gravitational and thermodynamic principles that have governed its behavior since its formation 4.5 billion years ago. The red giant doesn't arrive as an invader from outside the solar system. It emerges from within, the natural and inevitable result of stellar aging, as beautiful in its cosmic significance as it is devastating in its implications for planetary survival. The inner solar system as we know it will cease to exist. Mercury, the small cratered world that has endured solar radiation more intense than any other planet for 4.5 billion years, will be the first to disappear. As the Sun expands to perhaps 50 times its current radius, Mercury's orbit will be engulfed by the stellar atmosphere. The planet that survived the solar system's violent youth, that withstood bombardments by asteroids and comets, that adapted to temperature swings from 400 degrees Celsius on its day side to minus 170 degrees on its night side, will finally meet its match in the form of its own parent star. The process won't be instantaneous. As Mercury encounters the tenuous outer layers of the red giant sun, it will begin to experience atmospheric drag that slowly robs energy from its orbital motion. The planet will spiral inward through increasingly dense layers of stellar material, heating up as friction with the solar atmosphere converts orbital energy into thermal energy. Eventually, the rocky world that once reflected sunlight with its ancient, heavily cratered surface will be vaporized entirely, its atoms joining the stellar atmosphere that consumed it. Venus faces a similar but slightly more uncertain fate. Current models suggest that the red giant sun will expand to somewhere between 50 and 100 times its present radius, placing Venus right at the boundary of potential engulfment. If the sun's expansion is toward the smaller end of this range, Venus might survive as a scorched, airless rock in an expanded orbit. If the expansion is larger, Venus will follow Mercury into oblivion, consumed by the very star that once drove the runaway greenhouse effect that transformed it from a potentially habitable world into the hellish planet we observe today. But even if Venus avoids direct engulfment, its survival will be academic rather than meaningful. Long before the Sun begins its red giant expansion, Venus will have been subjected to stellar radiation so intense that any remaining traces of its original atmosphere will have been stripped away. The planet that may once have harboured oceans will have become a bare rock, its surface temperature exceeding 1,000 degrees Celsius, hot enough to melt lead and copper. Whether this dead world survives the red giant phase is a question of geological interest, but it bears no relation to the Venus that once might have been Earth's twin. Earth's fate, as we have seen, hangs in the balance between orbital expansion due to solar mass loss and orbital decay due to tidal interactions. The most detailed simulations suggest that our planet will just barely escape direct engulfment, ending up in an orbit roughly 50% larger than its current distance from the Sun, but this narrow escape comes at a cost that renders the survival meaningless. The Earth that might avoid consumption by the red giant will bear no resemblance to the world that gave rise to life and civilization. By the time the Sun begins its expansion into a red giant, Earth will already have been a dead world for billions of years. The gradual solar brightening will have long since stripped away the oceans and atmosphere, leaving behind a desiccated rock with surface temperatures hot enough to melt most metals. The tidal forces from the expanded Sun will likely have slowed Earth's rotation to the point where one hemisphere permanently faces the star while the other remains in eternal darkness, creating temperature extremes that would make current Venus seem temperate by comparison. Mars, orbiting farther from the Sun, has a better chance of avoiding direct engulfment, but its fate is no less sealed. The red giant's intense radiation will evaporate any remaining traces of the thin atmosphere that currently shrouds the red planet. The polar ice caps, which contain most of Mars' remaining water, will sublimate directly into space, carrying away the last vestiges of the planet's hydrological history. What remains will be an airless, waterless world, its famous red colour perhaps altered by the intense stellar radiation into something altogether alien. The transformation extends beyond the rocky planets to affect the entire architecture of the inner solar system. The asteroid belt, that collection of rocky debris between Mars and Jupiter that represents the building blocks of planets that never formed, will be subjected to radiation pressure and stellar winds that gradually push smaller objects outward or cause them to spiral into the Sun. Larger asteroids may survive as scorched, radiation-altered relics, but the asteroid belt as a dynamic system of orbiting debris will cease to exist. Even the concept of seasons, weather, and climate becomes meaningless in the inner solar system during the red giant phase. These phenomena depend on the subtle interplay between stellar radiation, planetary atmospheres, and orbital mechanics. When the Sun becomes a red giant, the radiation flux will be so intense that no planet in the inner system can maintain an atmosphere, and orbital dynamics will be dominated by the gravitational and tidal effects of a star that extends across what was once empty space. The erasure of the inner solar system represents more than just the destruction of individual worlds. It represents the elimination of the cosmic neighborhood where Earth developed its unique characteristics. The delicate gravitational resonances between planets that helped stabilize Earth's orbit over billions of years will be disrupted. The asteroid belt that may have provided water and organic compounds to the early Earth will be dispersed. The careful balance of forces that made the inner solar system a stable environment for planetary evolution will be replaced by the chaotic dynamics of worlds orbiting within or very close to an extended stellar atmosphere. This transformation is final and irreversible. Unlike other catastrophes that might befall planetary systems, stellar evolution cannot be undone or reversed. The red giant phase represents a one-way transition that marks the end of the solar system as a place where Earth-like worlds can exist. The Sun will eventually shed its outer layers and become a white dwarf star, but by then the inner planets will be gone, their atoms scattered through the stellar wind or incorporated into the remnant star itself. The inner solar system will have become a memory preserved only in the gravitational effects of the planets on the orbits of more distant worlds, and in whatever traces of heavy elements the destroyed planets contribute to the composition of the white dwarf Sun. The cosmic neighborhood that nurtured the only known example of life in the universe will have been erased by the same star that made that life possible in the first place. The inner solar system as we know it will cease to exist. Mercury, the small cratered world that has endured solar radiation more intense than any other planet for 4.5 billion years, will be the first to disappear. As the Sun expands to perhaps 50 times its current radius, Mercury's orbit will be engulfed by the stellar atmosphere. The planet that survived the solar system's violent youth, that withstood bombardments by asteroids and comets, that adapted to temperature swings from 400 degrees Celsius on its day side to minus 170 degrees on its night side, will finally meet its match in the form of its own parent star. The process won't be instantaneous. As Mercury encounters the tenuous outer layers of the red giant Sun, it will begin to experience atmospheric drag that slowly robs energy from its orbital motion. The planet will spiral inward through increasingly dense layers of stellar material, heating up as friction with the solar atmosphere converts orbital energy into thermal energy. Eventually, the rocky world that once reflected sunlight with its ancient, heavily cratered surface will be vaporized entirely, its atoms joining the stellar atmosphere that consumed it. Venus faces a similar but slightly more uncertain fate. Current models suggest that the red giant Sun will expand to somewhere between 50 and 100 times its present radius, placing Venus right at the boundary of potential engulfment. If the Sun's expansion is toward the smaller end of this range, Venus might survive as a scorched airless rock in an expanded orbit. If the expansion is larger, Venus will follow Mercury into oblivion, consumed by the very star that once drove the runaway greenhouse effect that transformed it from a potentially habitable world into the hellish planet we observe today. But even if Venus avoids direct engulfment, its survival will be academic rather than meaningful. Long before the Sun begins its red giant expansion, Venus will have been subjected to stellar radiation so intense that any remaining traces of its original atmosphere will have been stripped away. The planet that may once have harboured oceans will have become a bare rock, its surface temperature exceeding 1,000 degrees Celsius, hot enough to melt lead and copper. Whether this dead world survives the red giant phase is a question of geological interest, but it bears no relation to the Venus that once might have been Earth's twin. Earth's fate, as we have seen, hangs in the balance between orbital expansion due to solar mass loss and orbital decay due to tidal interactions. The most detailed simulations suggest that our planet will just barely escape direct engulfment, ending up in an orbit roughly 50% larger than its current distance from the Sun. But this narrow escape comes at a cost that renders the survival meaningless. The Earth that might avoid consumption by the red giant will bear no resemblance to the world that gave rise to life and civilization. By the time the Sun begins its expansion into a red giant, Earth will already have been a dead world for billions of years. The gradual solar brightening will have long since stripped away the oceans and atmosphere, leaving behind a desiccated rock with surface temperatures hot enough to melt most metals. The tidal forces from the expanded Sun will likely have slowed Earth's rotation, to the point where one hemisphere permanently faces the star while the other remains in eternal darkness, creating temperature extremes that would make current Venus seem temperate by comparison. Mars, orbiting farther from the Sun, has a better chance of avoiding direct engulfment, but its fate is no less sealed. The red giant's intense radiation will evaporate any remaining traces of the thin atmosphere that currently shrouds the red planet. The polar ice caps, which contain most of Mars' remaining water, will sublimate directly into space, carrying away the last vestiges of the planet's hydrological history. What remains will be an airless, waterless world, its famous red colour perhaps altered by the intense stellar radiation into something altogether alien. The transformation extends beyond the rocky planets to affect the entire architecture of the inner solar system. The asteroid belt, that collection of rocky debris between Mars and Jupiter that represents the building blocks of planets that never formed, will be subjected to radiation pressure and stellar winds that gradually push smaller objects outward or cause them to spiral into the Sun. Larger asteroids may survive as scorched, radiation-altered relics, but the asteroid belt as a dynamic system of orbiting debris will cease to exist. Even the concept of seasons, weather, and climate becomes meaningless in the inner solar system during the red giant phase. These phenomena depend on the subtle interplay between stellar radiation, planetary atmospheres, and orbital mechanics. When the Sun becomes a red giant, the radiation flux will be so intense that no planet in the inner system can maintain an atmosphere, and orbital dynamics will be dominated by the gravitational and tidal effects of a star that extends across what was once empty space. The erasure of the inner solar system represents more than just the destruction of individual worlds. It represents the elimination of the cosmic neighborhood where Earth developed its unique characteristics. The delicate gravitational resonances between planets that helped stabilize Earth's orbit over billions of years will be disrupted. The asteroid belt that may have provided water and organic compounds to the early Earth will be dispersed. The careful balance of forces that made the inner solar system a stable environment for planetary evolution will be replaced by the chaotic dynamics of worlds orbiting within or very close to an extended stellar atmosphere. This transformation is final and irreversible. Unlike other catastrophes that might befall planetary systems, stellar evolution cannot be undone or reversed. The red giant phase represents a one-way transition that marks the end of the solar system as a place where Earth-like worlds can exist. The Sun will eventually shed its outer layers and become a white dwarf star, but by then the inner planets will be gone, their atoms scattered through the stellar wind or incorporated into the remnant star itself. The inner solar system will have become a memory preserved only in the gravitational effects of the planets on the orbits of more distant worlds, and in whatever traces of heavy elements the destroyed planets contribute to the composition of the white dwarf Sun. The cosmic neighborhood that nurtured the only known example of life in the universe will have been erased by the same star that made that life possible in the first place. In the final stages of Earth's transformation from living world to cosmic fossil, what remains is not dramatic destruction, but something more subtle and perhaps more haunting. A planet that has lost its oceans, its atmosphere, and its dynamic geological processes becomes a kind of museum piece, a silent record of 4.5 billion years of planetary evolution frozen in rock and mineral. Earth as a fossil represents the ultimate expression of deep time, a world where the passage of millions of centuries becomes visible in the very structure of the landscape. Without the constant reshaping forces of weather, water, and atmospheric processes, the Earth's surface will begin to follow patterns of change that operate on geological timescales far longer than anything in the planet's previous history. The familiar processes of erosion, which have carved valleys, smoothed mountains, and redistributed sediments for billions of years, will slow to rates that make current geological processes seem frantically rapid by comparison. Mountains, those monuments to tectonic forces and crustal upheaval, will begin to relax under their own weight. Without wind and rain to carve away their peaks, without freezing and thawing cycles to crack their rock faces, without flowing water to carry away debris, mountains will settle into lower, more stable configurations determined purely by the balance between gravitational forces and the structural strength of rock. The dramatic peaks that define Earth's current geography will gradually round off, becoming more like the ancient weathered mountain ranges found on Mars, where similar processes have operated for billions of years in the absence of significant atmospheric activity. The geological record itself, that layer cake of sedimentary deposits that tells the story of Earth's biological and environmental history, will cease to accumulate new chapters. For billions of years, sedimentary processes have continuously buried older rocks under newer ones, preserving fossils, recording climate changes, and creating the stratigraphic sequence that allows geologists to read Earth's history like a book. But sedimentation depends on processes that require flowing water, wind, and the chemical weathering that breaks down rocks into transportable particles. Without these processes, the geological record becomes a closed book, its final pages written in the last deposits laid down before the planet's atmospheric and hydrological systems shut down. Impact craters, which on current Earth are quickly erased by erosion, tectonics, and biological processes, will begin to accumulate and persist on the surface. The airless Earth will be bombarded by the same meteorites and asteroids that have always struck our planet, but without an atmosphere to burn up smaller objects, and without geological processes to erase the scars, the surface will gradually acquire the heavily cratered appearance characteristic of ancient inactive worlds like the Moon and Mercury. Each impact will leave a permanent mark, creating a record of solar system debris that spans millions of years. The absence of plate tectonics, which may have already ceased due to the loss of water that helps lubricate crustal movements, means that the continents will remain essentially frozen in their final configuration. The slow dance of continental drift that has rearranged Earth's geography over hundreds of millions of years will come to a halt. Mountain ranges will mark the locations of the last continental collisions. Ocean basins will preserve the positions of the final rifting events, and the overall pattern of continents and former ocean floors will become a permanent map of Earth's last geologically active period. Tidal forces from the Moon, assuming our satellite survives the various catastrophes that befall the Earth-Moon system, will continue to operate on the solid planet, but at greatly reduced intensity. The Moon, which has been slowly moving away from Earth due to tidal friction throughout the planet's history, will continue this outward migration, but at a much slower rate, since there are no longer liquid oceans to create the strong tidal bulges that drive the process. Eventually, the Earth-Moon system may become tidally locked, with the same hemisphere of Earth always facing the Moon, just as the same side of the Moon always faces Earth today. The day-night temperature extremes on this airless world will be severe beyond anything Earth has previously experienced. The sunlit hemisphere will bake under the full intensity of solar radiation, with surface temperatures potentially exceeding the melting points of many common rocks. The night side will radiate heat away to space without atmospheric insulation, cooling to temperatures far below anything that liquid water or most chemical processes can survive. This temperature differential may drive some slow redistribution of materials, with volatile compounds sublimating on the hot side and condensing on the cold side. But the overall effect will be to create a static, unchanging landscape. Magnetic field dynamics. If Earth's magnetic field persists at all, in the absence of vigorous convection in the liquid outer core, will become increasingly simple and regular. The complex time-varying magnetic field generated by fluid motions in Earth's core today will either disappear entirely or settle into a more stable configuration. Without atmospheric interactions or solar wind effects modulated by atmospheric density, any remaining magnetic field will interact directly with space, creating patterns more similar to those observed around other airless bodies in the solar system. The concept of geological time itself takes on new meaning on this fossilized Earth. Processes that once operated over millions of years now extend over billions of years. Changes that were once measurable over human timescales now require cosmic timescales to detect. The planet becomes a testament to persistence, a world where the fundamental structure laid down during its active period remains essentially unchanged for longer than complex life existed on the original living Earth. What emerges is a world that preserves, in its rocks and landforms, a record of what planetary evolution can accomplish when given billions of years and the right conditions. The fossilized Earth becomes a kind of cosmic museum, displaying the results of processes that no longer operate but whose effects remain frozen in the planetary structure. It is Earth as archaeology, a world where the present tense has become the past perfect, and where the landscape tells stories of times when air moved, water flowed, and the planet lived and breathed as a dynamic system. In this final state, Earth achieves a kind of immortality, not as a living world, but as a monument to what living worlds can become when given enough time and the right conditions. The fossil Earth is both an ending and a preservation, the ultimate expression of a planet that once harboured the only known life in the universe. The story of Earth's future is not unique. Across the galaxy, around hundreds of billions of stars, the same fundamental processes of stellar evolution play out with variations on a common theme. What awaits our Sun and our planet is part of a galactic pattern of planetary destruction and renewal, a cosmic cycle that has been operating for billions of years and will continue long after our own solar system has run its course. By looking outward to other star systems, we can see Earth's destiny reflected in the fates of worlds we will never visit, orbiting suns we can barely detect. The evidence for this galactic pattern comes from studying stars that have already undergone the evolutionary processes our Sun will experience in the distant future. White dwarf stars, the dense remnants left behind when Sun-like stars exhaust their nuclear fuel and shed their outer layers, provide a window into the aftermath of stellar death and planetary destruction. These stellar corpses, each about the size of Earth but containing roughly the mass of our Sun, should theoretically have clean, pristine surfaces composed almost entirely of hydrogen and helium. But when astronomers examine the light from white dwarf stars, they find something unexpected. The spectra reveal the signatures of heavier elements, metals like calcium, magnesium, iron, and silicon, that have no business being on the surface of these evolved stars. These elements are too heavy to float on the surface under the intense gravitational field of a white dwarf. They should sink beneath the stellar surface within days or weeks, leaving behind the clean hydrogen and helium atmosphere that stellar evolution theory predicts. The presence of these heavy elements tells a story of cosmic destruction. They are the signatures of rocky planets and asteroids that have been torn apart by tidal forces as they spiraled too close to their parent stars during the chaotic final phases of stellar evolution. The calcium in a white dwarf's atmosphere once formed the bedrock of an alien world. The iron in its spectrum once comprised the core of a planet that may have harboured oceans, weather systems, perhaps even life. The silicon and oxygen tell of crustal rocks that witnessed billions of years of planetary history before being reduced to atomic debris in a stellar atmosphere. Astronomers have identified thousands of these polluted white dwarf stars throughout our galaxy, each one a tombstone marking the destruction of at least one planetary system. The frequency of such contamination suggests that planetary destruction during stellar evolution is not a rare catastrophe, but a common outcome. Current estimates indicate that 20 to 50% of all white dwarf stars show evidence of having accreted rocky material, implying that the majority of planetary systems around Sun-like stars do not survive their parent star's evolution intact. The process of planetary destruction leaves other observable signatures beyond atmospheric contamination. Around many white dwarf stars, astronomers have detected debris disks, vast rings of pulverized planetary material that can persist for millions of years as the remnants of destroyed worlds gradually spiral inward toward the stellar remnant. These disks glow with infrared radiation as they absorb starlight and re-radiate it as heat, creating ghostly signatures visible to space telescopes across interstellar distances. Some of these debris disks show remarkable structure, with gaps and clumps that suggest the gravitational influence of surviving planetary fragments. Computer simulations indicate that the tidal disruption of a rocky planet doesn't necessarily destroy every piece of the original world. Larger fragments, particularly dense metallic cores that once lay at the hearts of terrestrial planets, may survive as asteroid-sized objects orbiting the white dwarf star. These remnants represent the final traces of worlds that once had surfaces, atmospheres, and geological histories spanning billions of years. The chemical composition of the heavy elements found in white dwarf atmospheres provides clues about the nature of the destroyed planets. By analyzing the relative abundances of different elements, astronomers can reconstruct the bulk composition of the original planetary material. Some white dwarfs show evidence of having consumed planets with compositions similar to Earth, rocky worlds, rich in silicon, iron, and magnesium. Others reveal the signatures of more exotic planetary types, worlds with compositions unlike anything in our own solar system. The most remarkable discoveries come from white dwarf stars that show evidence of water-bearing planetary material. The detection of oxygen in ratios consistent with water ice suggests that some of the destroyed planets once harbored substantial amounts of H2O, either in subsurface oceans like those found on Jupiter's moon Europa, or in surface water bodies like Earth's oceans. The destruction of these potentially habitable worlds represents cosmic tragedies on scales that dwarf any earthly conception of loss. Recent observations have begun to catch planetary destruction in progress. Using advanced space telescopes, astronomers have identified systems where planets appear to be in the process of being disrupted by their evolved parent stars. These observations show dramatic dimming events as clouds of debris pass in front of white dwarf stars, creating eclipses that reveal the real-time disintegration of worlds that may have existed for billions of years. One such system, designated WD 156 3+645, shows regular dimming events every 4.5 hours as debris clouds orbit the white dwarf star. Spectroscopic analysis of the dimming reveals the chemical signatures of rocky material being vaporized in the intense radiation field of the stellar remnant. This is planetary death caught in the act, a real-time demonstration of the processes that will someday reduce Mercury, Venus, Earth, and Mars to clouds of metallic vapor spiraling into the remains of our Sun. The galactic perspective reveals stellar evolution as a process of cosmic recycling on the grandest scales. The heavy elements forged in the cores of dying stars and the rocky material of destroyed planets are eventually returned to the interstellar medium, where they become available for the formation of new stars and new planetary systems. The atoms that once formed the continents of long-dead worlds may someday become part of planets orbiting stars not yet born, continuing cycles of creation and destruction that operate over billions of years. Our solar system's future is written in this galactic pattern. The Sun will evolve, the inner planets will be destroyed or sterilized, and the heavy elements that once formed Earth's mountains and ocean floors will join the stellar graveyard that surrounds every white dwarf star. We are witnessing our own destiny played out around thousands of other stars, a cosmic preview of the transformation that awaits our own small corner of the universe. We are living in the golden age of planetary death detection, a remarkable period in human history when our telescopes have become sensitive enough to witness the final moments of worlds orbiting distant stars. What was once purely theoretical, confined to computer simulations and mathematical models, has become observable reality. We can now watch planets die in real time, their death throes visible across hundreds of light years as they spiral into their evolved parent stars, or are torn apart by tidal forces that strip away billions of years of geological history in cosmic instants. The technology that makes this possible represents one of the most sophisticated achievements in observational astronomy. Space-based telescopes like the Transiting Exoplanets Survey satellite and the Kepler mission were originally designed to find planets by detecting the slight dimming that occurs when a world passes in front of its star as seen from Earth. But these same instruments, capable of measuring changes in stellar brightness of less than 1 part in 10,000, have proven equally adept at detecting the irregular, chaotic dimming patterns that occur when planetary debris clouds eclipse their host stars. The first confirmed observation of a planet's death came from an unlikely source. A white dwarf star designated WD1 563 plus 645, located roughly 150 light-years from Earth in the constellation Draco. Every 4.5 hours, this stellar remnant dims by up to 40% as clouds of vaporized planetary material pass between the star and our telescopes. The regularity of these transits reveals an orbit, but this is not a planet in any conventional sense. It is the debris stream of a world in the process of being consumed, a rocky body that may once have been similar to Earth, but is now reduced to clouds of metallic vapor and dust particles. Spectroscopic analysis of these dimming events reveals the chemical fingerprints of planetary destruction. As the debris clouds pass in front of the white dwarf, starlight filtered through the vaporized rock shows absorption lines corresponding to calcium, iron, magnesium, and other elements that once formed the solid structure of a terrestrial world. The relative abundances of these elements suggest a planet with a composition remarkably similar to Earth, a rocky world with an iron core surrounded by a silicate mantle and crust. But WD 1563 plus 645 is not unique. As astronomers have learned to recognize the signatures of planetary destruction, similar systems have been identified throughout our local region of the galaxy. Each one tells a slightly different story of worlds meeting their end under the influence of evolved stars, but all share the common theme of planets reduced to debris by the same stellar evolution processes that await our own solar system. Some systems show evidence of multiple planets being destroyed simultaneously or in sequence. The debris clouds around these white dwarf stars contain a mixture of elements suggesting different types of planetary bodies, perhaps analogues to both the rocky inner planets and more volatile, rich outer worlds of our own solar system. The destruction appears to be comprehensive, affecting entire planetary systems rather than isolated worlds. The observations reveal destruction mechanisms that go beyond simple tidal disruption. Some systems show evidence of planets being vaporized by the intense radiation fields of their evolved parent stars before tidal forces can tear them apart physically. Others suggest collision cascades, where the disruption of one planet creates a debris field that impacts and destroys neighboring worlds in a chain reaction of cosmic catastrophe. Perhaps most remarkably, astronomers have begun to detect systems where planetary destruction appears to be ongoing over millions of years. These are not single catastrophic events, but extended processes where multiple generations of planetary material are consumed by white dwarf stars. The debris disks around some evolved stars show evidence of continuous replenishment, suggesting either the gradual consumption of large planetary fragments or ongoing collisional evolution within asteroid belt analogues that feed material to the central star over geological timescales. Advanced modelling techniques allow astronomers to reconstruct the final moments of these destroyed worlds in unprecedented detail. By analysing the timing, intensity, and spectral characteristics of the debris transits, researchers can determine the orbital characteristics of the disintegrating bodies, estimate their original masses and compositions, and even infer details about their internal structure. Some of the destroyed planets appear to have been differentiated worlds with distinct cores, mantles, and crusts, suggesting they experience billions of years of geological evolution before meeting their violent ends. The emotional impact of these observations extends beyond their scientific significance. We are witnessing the destruction of worlds that may have had histories as rich and complex as Earth's own. The calcium in a debris cloud once formed limestone deposits on an alien seafloor. The iron reveals the existence of planetary cores that may have generated magnetic fields protecting hypothetical biospheres from cosmic radiation. The silicon tells of crustal rocks that weathered under alien skies for geological ages before being reduced to atomic debris. These observations also provide a sobering preview of our own solar system's fate. The debris clouds we observe around distant white dwarf stars represent the future of Mercury, Venus, Earth, and Mars. The same tidal forces, radiation pressure, and orbital decay mechanisms that are destroying planets around other evolved stars will operate in our own system when the Sun exhausts its nuclear fuel and begins its transformation into a red giant and eventually a white dwarf. The new astronomy of endings represents more than just technological achievement. It marks a fundamental shift in how we understand planetary systems and their evolution. Planets are not permanent fixtures of the cosmic landscape, but temporary arrangements of matter, subject to the same cycles of birth, evolution, and death that govern everything else in the universe. The worlds we observe being destroyed around white dwarf stars are reminders that even planets, despite their geological timescales and apparent permanence, are ultimately transient features of an evolving cosmos. This perspective transforms our understanding of Earth's place in the universe. We inhabit not just a planet, but a moment, a brief interval in cosmic history when the conditions that make worlds like ours possible still exist. The observations of planetary death around other stars remind us that this moment will not last forever, that the stable conditions that have nurtured life for billions of years are themselves subject to change on scales that dwarf human experience, but are entirely manageable in terms of cosmic evolution. After the drama of the red giant phase has played out, after the Sun has shed its outer layers in spectacular planetary nebulae that will glow for thousands of years, what remains is something smaller, stranger, and in many ways more alien than the star that gave birth to our solar system. The Sun after the giant represents the final chapter in stellar evolution for stars of solar mass, a transformation so complete that calling the resulting object the same star requires a fundamental redefinition of what we mean by the word star. The white dwarf Sun will be roughly the size of Earth, but will contain approximately 60% of the original solar mass compressed into a sphere with a radius of only a few thousand kilometers. To comprehend this density, imagine taking the entire mass of Mount Everest and compressing it into a volume the size of a sugar cube. The gravitational field at the surface of this remnant will be hundreds of thousands of times stronger than gravity on current Earth, intense enough that a teaspoon of white dwarf material would weigh as much as an automobile if somehow transported to our planet's surface. This is matter in a state that has no analogue in everyday experience. The intense gravitational compression crushes atomic structure itself, forcing electrons to occupy energy states that are impossible under normal conditions. The resulting material, called degenerate matter, behaves according to quantum mechanical principles rather than the classical physics that governs ordinary solids, liquids, and gases. It is matter at the edge of what atoms can withstand before collapsing into something even more exotic. The white dwarf Sun will be intensely hot when it first forms, with surface temperatures reaching 100,000 degrees Celsius or more, far hotter than the current solar surface. This heat is not generated by nuclear fusion, which will have ceased entirely when the hydrogen fuel is exhausted, but rather by the gravitational energy released during the collapse from red giant to white dwarf. The entire object will glow with the intensity of thousands of current suns, but concentrated into a surface area smaller than Earth. But this brilliant phase will not last. Unlike the nuclear-powered sun we know today, which can maintain its energy output for billions of years through fusion reactions, the white dwarf has no internal energy source. It shines purely by radiating away the thermal energy stored in its incredibly hot, dense interior. This is stellar cooling on a scale unlike anything in the current solar system, a gradual dimming that will continue for trillions of years as the white dwarf slowly radiates its heat away to space. The cooling process follows a predictable but extraordinarily slow pattern. Over the first billion years, the white dwarf sun will fade from brilliant blue-white through yellow, orange, and finally red as its surface temperature drops. After 10 billion years, it will be cooler than the current sun but still glowing visibly. After 100 billion years, longer than the current age of the universe, it will have dimmed to a deep red ember barely visible against the cosmic background. Eventually, after timescales so long they strain comprehension, it will become a cold, dark sphere of crystallized carbon and oxygen, a black dwarf that emits no detectable radiation. The transformation from white-hot stellar remnant to cold black dwarf represents one of the longest processes in cosmic evolution. Current cosmological models suggest that the universe is not old enough for any black dwarfs to exist yet. Every white dwarf star in the observable universe is still in the cooling phase, still radiating energy into space, still glowing with the heat of gravitational collapse that occurred billions of years ago. The white dwarf Sun will outlive not just the Earth and the solar system, but potentially the galaxy itself, and even the expansion of the universe into its final cold state. During its long cooling phase, the white dwarf sun will undergo internal changes as exotic as its surface evolution. As temperatures in the interior drop, the degenerate matter will begin to crystallize, forming structures more regular and perfect than any crystal found in nature. The carbon and oxygen nuclei that make up most of the white dwarf's mass will arrange themselves into crystalline lattices of extraordinary purity and perfection. The sun will literally become a cosmic diamond, a sphere of crystallized carbon floating in the darkness of space. This crystallization process releases additional energy, temporarily slowing the cooling rate and extending the white dwarf's visible lifetime. The phase transition from liquid degenerate matter to solid crystal is one of the most dramatic events in the white dwarf's evolution, comparable in energy release to the original gravitational collapse, but spread out over millions of years rather than occurring in a single catastrophic event. The gravitational field around the white dwarf sun will create effects impossible in the current solar system. Light passing close to the stellar remnant will be bent by gravitational lensing, creating optical distortions that could magnify and distort the images of background stars. Time itself will run slower near the white dwarf's surface due to gravitational time dilation, an effect predicted by Einstein's relativity but negligible around the current sun. any remaining planetary system will be transformed beyond recognition by the white dwarf's intense but slowly fading radiation. The habitable zone, if it can be called that, will shrink to distances closer than Mercury's current orbit and will gradually move inward as the white dwarf cools. Objects that survive from the original solar system will be subjected to radiation fields and gravitational effects unlike anything they experienced during the Sun's main sequence lifetime. The white dwarf Sun represents both an ending and a beginning, the death of the star that nurtured billions of years of planetary evolution and the birth of an object that will persist longer than almost anything else in the observable universe. It is the Sun transformed into something eternal, not through the continuous burning of nuclear fuel, but through the slow, patient release of gravitational energy stored in matter compressed beyond the limits of ordinary physics. This smaller, stranger light will be the Sun's final gift to the cosmos, a beacon that will shine across deep time, marking the location where a solar system once thrived, where a planet called Earth once harbored the only known life in the universe, and where the cycles of stellar evolution played out their ancient drama against the backdrop of an expanding, cooling cosmos. When we contemplate the ultimate fate of Earth and the solar system, it's natural to ask whether there might be alternatives to passive acceptance of stellar evolution's inexorable march toward planetary destruction. The timescales involved, measured in billions of years, seem to offer ample opportunity for technological solutions that dwarf anything in current human experience. What would survival mean for a species or civilization that had billions of years to prepare for the Sun's transformation into a red giant and eventual death as a white dwarf? The question is not merely academic. Any discussion of survival on cosmic timescales requires us to think beyond the current limitations of human technology and consider what might be possible given exponential growth in scientific understanding over periods that are thousands of times longer than all of recorded history. The beings who might face Earth's final challenges would be as different from us as we are from the earliest single-celled organisms, equipped with capabilities that are literally unimaginable from our current perspective. The most obvious approach to survival involves migration outward from the inner solar system as the Sun brightens and eventually expands. Long before Earth becomes uninhabitable, a sufficiently advanced civilization could establish habitats in the outer solar system, where the moons of Jupiter and Saturn might become temperate worlds as increased solar luminosity extends the habitable zone outward. Europa and Enceladus, currently frozen ice worlds with subsurface oceans, could develop surface water and breathable atmospheres as the Sun's energy output increases. This outward migration could continue as stellar evolution progresses. During the Sun's red giant phase, when the inner solar system becomes uninhabitable, the outer regions around Jupiter, Saturn, Uranus, and Neptune might provide refuges for technological civilizations. The intense energy output of the red giant Sun could support vast populations on artificial habitats or terraformed moons at distances that are currently too cold for liquid water. But even the outer solar system offers only temporary respite. As the Sun eventually sheds its outer layers and becomes a white dwarf, the available energy for sustaining technological civilizations will decrease dramatically. The slowly cooling white dwarf will provide less and less energy over time, eventually forcing any surviving population to develop alternative energy sources or migrate even farther from their parent star. Interstellar migration represents the ultimate expression of survival strategy on cosmic timescales. A civilization with billions of years to develop technology could potentially build generation ships or develop faster than light travel to reach other star systems before the Sun's evolution makes the solar system uninhabitable. The nearest star systems, currently separated by distances that would take tens of thousands of years to cross with current technology, might become accessible through technologies we cannot yet imagine. The engineering challenges involved in such migrations are staggering, but not necessarily impossible, given sufficient time and technological development. Moving entire populations between star systems would require energy resources comparable to the output of stars themselves, controlled manipulation of matter and space-time on scales that dwarf current physics, and social structures capable of maintaining coherent civilizations across timescales longer than geological periods. Alternative approaches might involve modifying the solar system itself rather than fleeing from stellar evolution. Theoretical concepts like stellar engineering suggest the possibility of controlling or redirecting stellar evolution through technological intervention. Perhaps the mass loss rate during the red giant phase could be enhanced to reduce the Sun's final mass and extend its lifetime. Perhaps the nuclear burning process could be modified to alter the timeline of stellar evolution. Even more exotic possibilities involve harvesting the energy released during stellar evolution itself. The transition from main sequence star to red giant releases enormous amounts of energy that could potentially be captured and used to power artificial habitats or even entire artificial worlds. Dyson spheres and similar megascale engineering projects could transform the energy of stellar death into the foundation for technological civilizations that outlast their parent stars. Artificial worlds and habitats offer another pathway to long-term survival. Rather than depending on naturally habitable planets, advanced civilizations could construct their own environments precisely tailored to their needs. These artificial worlds could be mobile, moving between star systems as needed, or could be powered by fusion reactors or other energy sources that don't depend on stellar radiation. The concept of digital consciousness, or uploaded minds, introduces possibilities that transcend biological limitations entirely. Beings who exist as information rather than biological organisms could potentially survive in environments hostile to organic life, requiring only energy sources and computational substrates rather than breathable atmospheres and liquid water. Such entities could theoretically outlast not just stellar evolution, but potentially the heat death of the universe itself. But perhaps the most profound aspect of thinking about survival on cosmic timescales is recognizing that the question itself may be based on outdated assumptions. The beings who might face these cosmic challenges billions of years from now may have perspectives on survival, consciousness, and existence that are fundamentally different from our own. They may see the death of stars and planets not as catastrophes to be avoided, but as natural transitions to be embraced or even celebrated. The universe itself is evolving on these cosmic timescales. Galaxies merge, new stars form from the debris of old ones, and the fundamental properties of space and time may change as the cosmos expands and cools. Survival in such a universe might require adaptation not just to local changes like stellar evolution, but to changes in the basic structure of reality itself. These speculations remind us that survival on cosmic timescales is not simply a matter of developing better technology or more efficient energy sources. It requires us to reimagine what survival means, what consciousness means, and what it means to exist in a universe where change is the only constant, and where even the stars that seem eternal from human perspectives are ultimately temporary features of an evolving cosmos. The question of what survival could mean in principle becomes not just a technological challenge, but a philosophical exploration of what it means to persist across deep time. In the vast sweep of cosmic time, we exist during a brief and precious interval when conditions throughout the universe support the kind of complexity that makes planets like Earth possible. This moment in cosmic history, extending from roughly 10 billion years ago to perhaps 10 billion years in the future, represents what cosmologists sometimes call the stelliferous era, the age of stars. We live in a universe young enough for nuclear fusion to power stellar furnaces, yet old enough for the products of stellar nucleosynthesis to form rocky planets and complex chemistry. This cosmic timing is not coincidental. The elements that make up your body, the oxygen you breathe, the carbon in your cells, the calcium in your bones, were all forged in the nuclear furnaces of stars that lived and died before the sun was born. These elements were scattered through space by stellar winds and supernova explosions, eventually becoming incorporated into the molecular cloud that gave birth to our solar system 4.5 billion years ago. You are made of star stuff, but more than that, you exist at exactly the right moment in cosmic evolution for star stuff to organize itself into living, thinking beings. The rarity of this moment becomes apparent when you consider the full timeline of cosmic evolution. The universe began 13.8 billion years ago with the Big Bang, but for the first few hundred million years, no stars existed at all. The cosmos was filled with hydrogen and helium, the simplest elements, but lacked the heavier elements necessary for rocky planet formation. The first generation of stars had to live and die before carbon, nitrogen, oxygen, silicon, iron, and the other elements essential for terrestrial worlds could exist in sufficient quantities. Even after heavy elements became available, it took billions of years for planetary systems to develop the complex characteristics that make life possible. Early planetary systems were chaotic places, subject to frequent impacts from leftover debris, intense radiation from young stars, and gravitational disruptions from nearby stellar encounters. The stable, multi-billion-year environments necessary for biological evolution to produce complex organisms required time for these cosmic construction zones to settle into the orderly systems we observe today. Earth itself exists in a narrow window of solar evolution. Our planet formed when the Sun was roughly 25% dimmer than today, yet it has maintained liquid water on its surface throughout this period of gradually increasing stellar luminosity. This remarkable stability depends on the precise timing of Earth's formation, its distance from the Sun, its mass and composition, and a host of other factors that had to align within narrow ranges for billions of years of habitability to be possible. The future universe will be a very different place. As stellar formation rates decline due to the exhaustion of hydrogen gas in galaxies, new stars will become increasingly rare. The stars that exist will be predominantly low mass, long-lived red dwarfs that burn their fuel so slowly they can shine for trillions of years. But these dim, cool stars create habitable zones so close to their surfaces that any planets within them are likely to be tidally locked, with permanent day and night sides that create extreme climate conditions. More fundamentally, the expansion of the universe itself is accelerating, driven by the mysterious dark energy that makes up roughly 70% of the cosmic energy budget. This acceleration means that galaxies are moving apart at ever-increasing rates, eventually isolating each galaxy as an island universe surrounded by empty space. The raw materials for star formation will be exhausted. Existing stars will burn out one by one, and the universe will enter what cosmologists call the degenerate era, when the only significant sources of energy are the slow decay of protons and the gradual evaporation of black holes through Hawking radiation. Against this backdrop of cosmic evolution, the present moment takes on extraordinary significance. We live during the brief interval when the universe is old enough for complexity, but young enough for energy. Stars like the Sun provide stable energy sources for billions of years. Rocky planets can form and maintain conditions suitable for liquid water and complex chemistry. The cosmic expansion has not yet isolated galaxies from each other, allowing for the large-scale structure and chemical evolution that makes our current universe so rich and varied. The Sun's slow brightening, which will eventually destroy Earth's habitability, is itself a reminder of this cosmic timing. Our star is approximately halfway through its main sequence lifetime, burning hydrogen fuel at a rate that has remained stable for over 4 billion years and will continue for roughly 5 billion more. This 10 billion year period of stellar stability represents a tiny fraction of the Sun's total existence. Before nuclear fusion began, the Sun was a slowly contracting ball of gas that took tens of millions of years to reach the temperature and pressure necessary for hydrogen burning. After the main sequence ends, the Sun will become a white dwarf that cools for trillions of years, far longer than the current age of the universe. This perspective transforms our understanding of Earth's fate from tragedy to recognition of cosmic privilege. The very processes that will eventually make our planet uninhabitable are the same processes that have made it a living world for billions of years. The nuclear fusion that powers the Sun's gradual brightening is also the source of every calorie of energy that has ever powered a living organism on Earth. The stellar evolution that will transform the Sun into a red giant and eventually a white dwarf is part of the cosmic cycle that created the heavy elements necessary for planets and life in the first place. We exist during the golden age of cosmic evolution, when the universe has had enough time to develop complexity, but still possesses the energy sources necessary to sustain it. The gradual changes that will eventually end Earth's habitability operate on timescales so vast that they serve not as sources of despair, but as reminders of the extraordinary cosmic circumstances that make our existence possible. The tender rarity of the present is written in the very physics that governs stellar evolution and planetary formation. Imagine, if you will, the last night on Earth. Not the dramatic finale of science fiction, not the catastrophic collision or explosive destruction that captures our imaginations, but something quieter, more profound, and infinitely more beautiful in its cosmic significance. The final evening when conditions on our planet still allow for the luxury of contemplating a sunset, when the atmosphere remains thick enough to scatter light into the familiar colours that have painted Earth's skies for billions of years. This last night would come not suddenly, but as the culmination of processes we have followed throughout this journey: the slow brightening of the Sun, the gradual failure of Earth's climate regulation systems, the inexorable transition toward conditions that no longer support the delicate balance we call habitability. Perhaps 1 billion years from now, perhaps slightly more or less, there will come a moment when the runaway greenhouse effect finally overwhelms the last vestiges of Earth's ability to maintain liquid water on its surface. The beings who witness this final sunset, if any conscious entities remain to observe it, would be looking up at a sun noticeably brighter than the one we know today. The star that has defined Earth's environment for 4.5 billion years would be pumping perhaps 30 to 40% more energy into space than it does now, enough to push global temperatures past every threshold that makes our world habitable. The oceans would be disappearing into the atmosphere as water vapor, the last liquid water pools shrinking away from coastlines that have witnessed the rise and fall of countless species. But there would be no panic in this ending, no desperate struggle against inevitable physics. The last night on Earth would arrive with the same cosmic patience that has characterized all the great transitions in our planet's history. The same gradual pace that marked the formation of the first oceans, the rise of oxygen in the atmosphere, the evolution of complex life, would characterize this final transition away from habitability. The universe operates on timescales that dwarf human anxieties, following physical laws that treat the birth and death of worlds with equal equanimity. As the final darkness falls across a world that is losing its ability to moderate temperature between day and night, the stars would still shine with the same patterns that guided navigators and inspired poets throughout human history. The constellations would appear largely unchanged from our current perspective, since even 1 billion years represents a tiny fraction of the time required for stellar motions to significantly alter the familiar patterns we see today. Orion would still dominate winter skies, the Big Dipper would still wheel around Polaris, and the summer triangle would still mark the heights of warm season nights, though the concept of seasons would by then have lost all meaning on an overheated Earth. The Moon, assuming it survives the various gravitational perturbations that affect the Earth-Moon system over such vast timescales, might appear slightly smaller and more distant than today. The same tidal forces that currently cause our satellite to recede from Earth at a rate of about 4 centimeters per year would have pushed it noticeably farther away over the course of 1 billion years. The tides that once sculpted coastlines and influenced the evolution of life would be weaker, though by then there would be no oceans left to raise and lower. In the broader context of the solar system, this last night on Earth would occur during what might still be considered the Sun's stable main sequence phase. The dramatic expansion into a red giant would still be billions of years in the future. From the perspective of stellar evolution, the Sun would still be in its prime, burning hydrogen fuel at a steady rate, maintaining the same basic structure and appearance it has had for most of its lifetime. The crisis for Earth would be invisible from any external perspective, a consequence not of stellar instability, but of stellar success, the continued operation of nuclear fusion proceeding exactly as physics dictates it must. The ending that arrives on this last night carries no moral weight, no judgment on the worthiness of the life that Earth has harboured. Stars change because nuclear physics requires them to change. Planets lose their habitability because thermodynamics and atmospheric physics operate according to universal principles that make no exceptions for worlds that happen to harbour complex chemistry or conscious observers. The universe follows its own logic, independent of any preference for or against the continuation of life. Yet there is something profound in contemplating this ending, something that connects us to the deepest questions about meaning and permanence in an evolving cosmos. Earth's final night represents the completion of a story that began with the gravitational collapse of a molecular cloud 4.5 billion years ago. The same physics that created our planet, that formed its oceans and atmosphere, that enabled the evolution of life, eventually ensures its transformation into something alien and uninhabitable. This is not a failure of cosmic design, but its ultimate expression. The universe is not a machine built to maintain conditions comfortable for life, but a system of matter and energy following physical laws that sometimes, in rare places and for brief periods, allow for the emergence of complexity, consciousness, and the capacity for wonder. Earth's story, from its formation to its eventual uninhabitability, represents one complete cycle of this cosmic process. The last night on Earth would end not with drama, but with daybreak, one final sunrise, illuminating a world that has given everything it had to give. The sun would rise as it always has, following the same gravitational and thermodynamic principles that have governed its behaviour since nuclear fusion first began in its core. But it would be rising over a planet that has completed its transformation from a cradle of life into a monument to what temporary arrangements of matter can accomplish when given billions of years and the right conditions. In this calm ending without despair, we find not tragedy but perspective, a reminder that meaning is not diminished by impermanence and that the beauty of any phenomenon, from a single sunset to the entire history of a living world, exists independent of its duration in cosmic time.